In our video today, we're going to move on and explore logarithmic functions from section 4.3. We last focused on the exponential function. Every one-to-one function has an inverse that is also a function. Now, we know that to be a function, it has to pass the vertical line test. So, for example, here's my quadratic function, f of x equals x squared. This is going to pass my vertical line test. Any vertical line I draw will only pass through that parabola once. To be a one-to-one function, it also has to pass a horizontal line test, because to be a one-to-one function, that means that each value in the domain, each x value, corresponds to a unique y value. That addition of the word unique makes it one-to-one. That means that not only do I not repeat x values, but I also do not repeat y values. To be a one-to-one function, it is going to end up passing both our vertical line test and our horizontal line test. So this quadratic is a function because it passes my vertical line test. It's a function. But it fails my horizontal line test, so it's not one-to-one. Now, what does that mean? Well, I can invert anything. I can find the inverse of any relation. But for that inverse to also be a function, I have to start with a one-to-one function. Exponential functions are examples of one-to-one functions. Their inverses, therefore, are also going to be functions. Their inverse, in the case of the exponential function, is a log function. How do we find the inverse of a function? Well, we're going to use what we call the switch and solve method. Switch and solve. And we'll walk through that today. When we do the switch and solve method, we exchange the domain and range. We exchange the domain and range. Alright, so let's see what this looks like as a graph. Here we have an exponential function and its inverse log function. They're the same base. My base is 2 in both instances. Now you guys know how to graph this exponential function. When we graph exponential functions, we start with those 5 basic x values from -2 to 2. Remember that negative exponent tells me to take the reciprocal. So 2 to the -2 power is 1/4. 2 to the -1 power is 1/2. Anything to the 0 power is 1. 2 to the first power is 2, and 2 squared is 4. This is my y-intercept. Graph that right there. I know that my function's going to flow upward just like that. I have a horizontal asymptote. At y equals 0. My exponential function always has a domain of all real numbers, and the range is limited by that horizontal asymptote. So for the parent function, it's limited from 0 to infinity. That's my base function, my exponential function. The inverse of that is going to have a switch, the domain and range, exchange our domain and range. So my domain of the exponential function becomes the range of the inverse function, -infinity to +infinity, and the range of the exponential function becomes the domain of the inverse function from 0 to +infinity. That also, I can make that switch in my ordered pairs so that my x column becomes my y column, and my y column from the exponential function becomes my x column. Now when I get ready to graph this point that was my y-intercept, because x was 0, is now my x-intercept. Because now, since I switched the domain and range, y is 0. So let's graph that. The point 1, 0 is right here. I see that if I move back to these fractional x values, I'm down here at -2, So instead of approaching a horizontal asymptote, I'm approaching a vertical asymptote. And then I've got 2 to the first power, 4 not 2 to the first power, 2 and 1, and then the 0.42. And this is what my logarithmic function looks like. You'll notice that the curve is the same, but now I have a vertical asymptote, a limit on domain, vertical asymptote at x equals z, not x equals y, x equals 0. And I have to watch myself today. I can't talk and write at the same time. At x equals 0 for my log function. Now you will also notice that these two functions mirror each other along this line of reflection, y equals x. Any function and its inverse will reflect across this positive linear function with a slope of 1, y equals x, through the origin. They're always going to reflect across that line. That happens because of that exchange of domain and range to get from the function to its inverse. Now, when I am graphing a log function, a lot of the times I will start with the exponential function in the same base and then make that switch. So I'll set up my ordered pairs this way because this is easier for me to calculate, and then I will switch the columns to figure out what points I need to graph. When I'm talking about exponential functions, or excuse me, logarithmic functions, remember that the answer to the log function is always the exponent of the base. So when I'm given a log function, what I'm asking for is the exponent. This definition of logarithm we're going to use a lot. The definition of logarithm tells us that we can switch back and forth, these are exchangeable, from the log form to the exponential form. So when I refer to the definition of logarithm, this is what I'm talking about. That if I have a log equation, I can rewrite that as an exponential equation, and vice versa. If I have an exponential equation, I can rewrite it as a log equation. Being able to switch that back and forth allows us to solve a lot more equations simply. Now let's break that switch back and forth down. There are 3 pieces of information that are going to switch places when we're converting back and forth from an exponential function to its inverse logarithmic function. Now we're most familiar with our exponential function, so we're going to start here. With our exponential function, we have a base raised to an exponent, and I'm going to color code this. A base raised to an exponent, and that gives me an argument. Now my example is going to be something familiar. We're going to say 2 cubed, and that is equal to my argument 8. And again, I've got my color coding going on. Base raised to an exponent is equal to an argument. This is my exponential form. My definition of logarithm tells me that it has an equivalent logarithmic form, and I can switch back and forth. Log, and then down here is my base. That subscript is where I put the base. And then the log base whatever of my argument is going to be equal to, what did I tell you the answer to the logarithm was? The answer is the exponent. So log base of the argument is equal to the exponent. That means I take this 2 cubed is equal to 8, and to put it in logarithmic form, I have my base down here, subscript, argument is equal to the exponent. These two equations are equivalent statements. They mean the same thing. They give us the same information. To read this, I say log base 2 of 8 is equal to 3. The question I ask myself, what is the exponent of 2 that gives me 8? So I would say, what is the exponent of 2? There's my unknown that gives me 8. Well, that exponent is 3. 2 cubed is 8. All right, let's practice going back and forth. Now that's all that some of these ask you to do is literally to go back and forth. We're going to write our exponential equation in logarithmic form. So my exponential equation here, 4 to the negative 3 is equal to 1/64. That is true. To write it in log form, I put my base as the subscript, the argument next to the base, and that's always going to be equal to the exponent. So these are equivalent ways of saying the same information. Log base 4 of 164 is equal to -3. This next exponential form says 6,561 to the 1/4 power, that's an exponent, is equal to 9. 1/4 is the exponent of 6561. Remember that rational exponent tells you that I'm taking a root? So another way to write that would be the 4th root of 6,561 is 9. You could check that with your calculator if you wanted, but we're wanting the log form. What's my base? Well, the base of the exponent is the 6561. What's the argument? That's 9, and that's equal to my exponent of 1/4. Anything to the 0 power is 1. When I write this in log form, my base here is 5. If you can't remember what goes where, remember, oh, the answer is the exponent. So that 0 has to go over here, which means that's where the 1 should be. These other 3 are going to go the other direction. Now we're given our log form, and we're going to put it in exponential form. Let's see if I can get that a little more clear. We're given the equation in log form. We want to put it in exponential form. So what is your base? Well, log, the base is that subscript right there. The base is 2. The answer to the log statement is the exponent. So the 3 goes here, and that's equal to, that makes this the argument. 2 cubed is 8. Now we know that is true. 2 cubed is 8. Right here, what is the exponent of 3 that gives us 81? Well, it's 4. I can rewrite that as 3 to the 4th is 81. Some of these we can reason out because we know how to raise numbers to powers. But what if we have variables involved and we have unknowns? Well, then we have to remember how those pieces switch back and forth. Right? What is my base here? Well, my base is b. B to what power? Well, the answer to the log statement is always the exponent. That's going to be equal to the argument. All right, let's do a little bit of practice together. I would really like for you to pause the video and see if you can answer these log functions. So remember, we are looking for the exponent. That's the answer that we're looking for. So pause the video, see what you can do on your own, and then come back. This first row is pretty easy. What's the exponent of 3 that gives me 9? Well, that's going to be 2. And you may need to come up here and say, okay, 3 to some power equals 9, and my missing piece is that 2. Right here, 5 to some power is 625. Well, that's 5 cubed. Right here, 6 to some power is 216. That is also, oops, I looked ahead. 5 cubed is 125, not 625. I hope you were all sitting there yelling at me. 5 to the 4th power is 625, but 6 cubed is 216. Now this next one looks a little weird because I see that my argument is smaller than my base. So what I'm asking is, what is the exponent of 9 that gives me 3? Well, 3 is the square root of 9. So what I need to do is say, okay, that's going to be square root 9 is 3. Well, how would I write that square root 9 as an exponent? Remember, a fractional exponent gives us radicals. Do you see anything else that's going to need a fractional exponent on these? I don't see any other fractional exponents. So let's look at number 5. 2 to what power gives me a -4? Ooh. Can I raise a positive 2 to any power and end up with a negative result? I just can't. To positive 2 multiplied by itself however many times is always going to be a positive result. My argument here is never going to be negative. That is just not possible. Another way to say not possible would be to say DNE does not exist. What about this one? 3 raised to what power is 0? Well, anything to the 0 power is 1, but can I multiply 3 times itself a certain number of times and get 0? That one does not exist either. It's not possible. The rest of these are all possible. Here, I see that my argument is a fraction. So I'm looking for an exponent of 2 that gives me 1/4. Well, I know that 2 squared is 4. What would I do to that exponent 2 to give me a 1/4? Well, that's going to have to be a negative exponent. Anytime you see a fraction as your argument, look for a negative exponent, like number 8 here. Oh no, that has the fraction as the base. That's still going to work the same way. I've got a fraction as one or the other. 1/2 to what power gives me 8? Well, if I cube it, I would have 1/8. If I raise it to the -3, that flips, and I have 8. Right here, 4 squared is 16. 4 to the -2 is 1/16. Right here, 4 to the first is 4, but 4 to the -1 is 1/4. 4 to the what is 1/4. Right here, 9 to the -2 is going to be 1/81. This is my last one. What is the exponent of 7? That gives me 49. Well, 7 squared is 49. Okay, those are some great practice problems. Help you start getting the hang of how to do things in your head. Notice that we're doing a lot of mental math, hopefully not grabbing your calculator. And for a lot of these, I want you to know how to do them without relying on your calculator. There isn't an any base log button on your calculator, but you can evaluate logs in 2 special bases. If you look at your calculator, I've got 2 logarithm buttons right here. LOG is my common log, LN is my natural log, and if you look at the second function value just above the button, you can see what their individual bases are. LOG log is common log, it's base 10, and natural log is LN, and it is base E. Remember, E is our irrational constant, like pi is an irrational constant, E is an irrational constant. That's my base of my natural log. Anything base 10 or base E, I can just plug into my calculator and solve. So, oh, look at this though. We're asked to do common logs without using our calculator. Well, common log is base 10. Notice that when I have LOG log, no base written, that's when I know it's a common log base 10. So I'm still asking for an exponent. So my base is understood to be 10 here. I'm asking, what is the exponent of 10 that gives me 1,000? Now, hopefully, maybe you remember that when I raise 10 to a power, I can just count the zeros. 10 to the first is just 10, 1 0. 10 squared is 100, 2 zeros. 10, getting ahead of myself, words and hands not matching again. 10 cubed is 1,000, 3 zeros. 10 to the 4th, etc., etc. So here I have 1,000, that's going to be 3 zeros, so that would be 10 cubed. Here I have 1, 2, 3, 4, 5, so that would be 10 to the 5th power is 100,000. Ooh, we're going back the other way. Decimal, tenths, hundredths, thousandths. So this is log of 1,000th. Well, log of 1,000 is 3. How do I get log of 1,000th? I make that a -3. How do I know these are all common logs? Well, when I look at my log statements, I see that I have LOG written with no base. My base is understood, let's say no base given. It has a base. No base given. No base written. No base given. It has a base, it's just understood. Just like when I see a radical and there's no index given, I know that my index is 2, that's a square root. When I have LOG log with no base given, I know that that's common log base 10. If it's a natural log, it's a base E. And these, we are going to use our calculator round to 3 decimal places. So natural log of 1 is 0. Anything to the 0 power is 1. You could have done that without your calculator. Can't do this one without your calculator because natural log is not base 10. If I do natural log of 10, I get this irrational number. I need to round to 3 decimal places. 1, 2, 3. This is 2. The next decimal is a 5. It's halfway there, so it's going to round up. So that would be 2.303. Natural log of -6. Hopefully you have some red flags going up. Natural log of -6, it says domain error. Why? Well, remember back on that last page, we said that these were not possible because this one is not possible because any positive value, and my base has to be positive, cannot raise that to an exponent and ever end up with a negative argument. So because my base is always positive, that means my argument will always be positive. I will never have a negative argument. We'll never get a negative argument, and that's because the base must be positive. Must be positive. Okay. How do I know these are all natural logs? Well, because that is written as ln, which is natural log base e. There is not an any base logarithm button on your calculator. If we want an exact answer for something that is not base e or base 10, we have to leave it as a logarithm usually. But if we need to find an approximation, like this is an approximation, and use our calculator, we're going to use our change of base theorem. Now, change of base theorem can be used with either of my log buttons on the calculator, base 10, common log, or base e, natural log. It does not matter which one. This is written as just natural log. I could also say just like this. Now, what you need to notice for my change of base formula, you're given a log statement where your base is not common or natural, not 10 or e. That base goes on bottom. Base goes on bottom. That's what's important. And then the argument goes on top. Whichever of the two I choose, I do the same log button, numerator and denominator. So it's either natural log over natural log or common log over common log. And your key to remember here is that the base goes to the bottom. It alliterates. That's your denominator. We're going to practice that change of base property to simplify or solve and find an approximate value where we round our answers to 2 decimal places this time. So I do not have a base 3 log button on my calculator, but I'm going to use the change of base formula. Now I know that some of you may have calculators that will do change of base stuff without you doing it. I want you to be able to give me your change of base formula. So whether your calculator has a special way to plug this in and it will work it for you or not, you have to show me this next step. So make sure that you write this down. I can use either common log or I can use natural log. You don't have to do both, but I have a 3 and a 56. The 3 is the base, so it goes on bottom. That means the 56 goes on top. When I calculate this, I'm going to have to remember to use parentheses. So let's say we use our natural log. Natural log 56 is in the numerator. I'm going to close that, and then I'm going to divide by natural log 3 in my denominator, and that gives me 3.66 rounded to 2 decimal places. Now let's look at something. If I chose to go common log instead of natural log, if I did common log 56, close parentheses, divided by common log 3, enter, I get the same value. What if I forget to close my parentheses? Let's say I do common log 56 divided by common log 3. My order of operations is wrong right there. It gives me a different answer because I used the wrong order of operations. So you have two choices. You can either hit enter and then divide by the other value that goes in the denominator, and that works, or you have to remember to close those parentheses. So I want you to work through the other 3. Oh, let's just do this one. These are in the other form. Let's do this. So here I need to simplify. We're going to do common log first. My base goes on bottom, so 0.2 is my denominator, 9 is the numerator. If you plug that in correctly and round it, you will get about, that's why I do a wavy equal sign, a negative 1.37. I do that if I do natural log 9 divided by natural log 0.2. 1.37 is what it rounds to 2 decimal places. That rounding is important. Make sure you round correctly. These last two, I'm starting in exponential form. I need to know the exponent that I raise 5.44 to that gives me 2.3. Well, I have no idea. That makes no sense to me. I can't solve for x in the exponent. This is where I'm going to use my definition of logarithm. My definition of logarithm to put this in log form. LOG. What's my base? Well, my base is that 5.44. of the argument 2.3, and I'm looking for that exponent x. So this gives me the log statement that I need to simplify. X is going to be, and then let's go ahead and do common log this time. Base goes in bottom, 5.44, 2.3 in top. I want you to be able to show me this step. No matter what your calculator requires, you need to be able to write this down and know how to set it up. And this is what you should get approximately. For this one, again, I need to rewrite it in log form. So I'm going to say log log. Base is 10, so I don't have to write that base down there. That's understood. Log of 3.91 equals x. That's a common log. I can plug that straight into my calculator and get an approximate value for x of 0.59. All right, very good. Let's look at this last page. I hope you always remember that you can go through and you can pause, rewind, rewatch, listen again. I know that I'm going quickly, but I'm going quickly because you have control over these videos as you watch them. Properties of logarithms. These are some things that if you understand, you can answer some of your log problems quickly. These are things you need to know and remember. We've got 4 different values, A, B, C, and D, and this looks really small. I need to blow that up. But we're just going to go with it as it is for right now. So let's look at some examples of these. Log base A of 1 equals 0. So for A, for this first one, log base A of 1 equals 0. A can be anything. So let's just say log base 17 of 1 equals 0. What is the exponent of 17 that gives me 1? Well, it's 0. Anything raised to the 0 power is 1. So anytime I see that 1 as my argument, I know that the exponent would be 0. B over here, log base A of A is equal to 1. So in essence, log base 12 of 12. What is the exponent of 12 that gives me 12? Well, it's 1. Anytime you see that the base and the argument match, they're the exact same thing, my answer, my exponent, is going to be 1. What does C tell us? Log base A of A to the R power is just that exponent R. So let's put some numbers on that. Log base 5 of 5 cubed is what? Well, let's put it in that rewritten form that I did. So I say, okay, my base raised to some exponent, that's my missing piece, is equal to this argument 5 cubed. Well, what's my missing piece? My missing piece is that exponent. So when this base matches this base, the answer is that exponent. And then finally, my last property here, A raised to the power log base A of x equals x. Over here, just like A and A are the same, this base is the same as this base. When this base is the same as this base, the answer is that argument. So let's do 2 raised to the log base 2 of x. What's that going to be equal to? Well, this base matches this base, so my answer is going to be that x. More rules for logarithms. Remember that logarithms are the inverse of exponential functions. This means that my properties for logarithms are going to mirror, they're going to be really directly related to our rules for exponents. So let's review our rules for exponents. Product rule. Product is the answer to a multiplication problem. When you're multiplying the base, we add the exponents. That's what this looks like. An example with numbers, 2 cubed times 2 to the 4th would be 2 to the 7th. When I'm multiplying the base, I add the exponents. Why does this work? Well, that would be 2 cubed is 2 times 2 times 2, right? 2 to the 4th is 2 times 2 times 2 times 2. I'm multiplying 2 times itself 7 times. Quotient rule. Quotient is an answer to a division problem. When I'm dividing the base, what do? Well, multiplication is repeated addition. Division is repeated subtraction. So if I'm going to divide the base, I subtract the exponents. So to extend this problem, if we have 2 cubed divided by 2 to the 4th, that's going to be the same thing as subtract the exponents, numerator minus denominator. 3 minus 4 is -1, and 2 to the -1 is 1 over 2. Let's take a little bit different look at that. Let's do 2 times 2 times 2 in my numerator, 2, 2, 2, 2 in my denominator. Anything over itself is 1, right? So that's 1, that's 1, that's 1, and it leaves me with 1/2 left over. 1, 1, 1, and one other 2 in the denominator. Power rule tells me that when I raise an exponent to a power, I'm going to multiply the exponents. Now, this is different from my product rule. In my product rule, I have that base repeated, 2 to something, 2 to something. With my power rule, I only have the base written once, but I have an exponent raised to another exponent. In this case, I'm multiplying those exponents together. We're going to use these rules for logarithms to help us expand and condense our log statements. Expand means we stretch them out. Condense means we squish them up together. We're going to expand and condense our log statements to see if we can simplify any of the expressions. Sometimes I will give you things that will simplify. Some things we are just doing it to practice. We have, just like with rules for exponents, we have product, quotient, and power rule. We have rules for logarithms, product, quotient, and power properties. My product property tells me if I am multiplying in the argument, I split it apart and show addition between two separate log statements. Quotient property tells me if I'm dividing in the argument, I split it apart and show subtraction, because division pairs with subtraction, multiplication pairs with addition. And my power property says that if my argument has an exponent, I can bring that exponent out front. That's my power property. So and these work either direction. I can move from the left side to the right side, or I can start with the right side and move back to the left side. So let's expand by moving from the left side to the right side. Well, what am I doing here in my argument? In my argument, I'm dividing. Division is quotient, and division pairs with subtraction. So I'm going to split this apart. I've got log base 3, and then I start with my numerator, minus still log base 3, and then my denominator. So numerator minus denominator, I copy that log base 3 with both log statements. Now I need to look at those log statements and see if I can simplify either one of them. Well, this first one is going to simplify. What is the exponent of 3 that gives me 27? Well, 3 cubed is 27. Is there an exponent of 3 that gives me 4? No, I can't simplify that statement. So that's what I end up with. All right, this next one. I am multiplying in this argument, so multiplication is product rule. Product rule, multiplication pairs with addition, so I can split it apart. How many things am I multiplying here? Well, I've got a 3, I've got an x squared, and I've got a y. So when I split it apart, I'm splitting it apart into 3 separate log statements and showing that they are all being added together. Can I simplify anything else? Well, this second log statement has an exponent, so I can apply my power rule or power property here by pulling this exponent in front just of this second log statement. So what I end up with, what I'm left with, is natural log 3 plus 2 times natural log x plus natural log y. And that's all I can do. I can't simplify any of those. That's as far as that one goes. That was just practice. Now, this is moving from left to right where I'm expanding, but if I start with multiple log statements and I want to condense them back into a single log statement, I am starting on the right and I'm moving back to the left. So we're going to condense. Here we were expanding, now we're going to condense. I've got 2 separate log statements. They're both the same base. LOG log with no base written is base 10. I can write it, they're paired by addition. Addition pairs with multiplication. That's my product rule. So I've got LOG log, and then I multiply those arguments together. Well, 25 times 4 is 100. Can I simplify that? What is the exponent of my base? My base is 10. What's the exponent of 10 that gives me 100? Well, the exponent of 10 that gives me 100 is 2. And then finally, oh, this was a fun one. I need to clean this all the way up. I have an exponent, power rule here. I have power rule here. I want you to notice that in this one, my argument is x plus 5. I don't have a rule for addition in the argument. There's not anything I do with this argument to split it apart or pull it apart. X plus 5 is the argument, it just stays x plus 5 as my argument. That's all there is. I see that I'm adding these two together, but let's do that power rule first. So I've got natural log of x squared plus natural log of x plus 5 to the 1/3 power. Now I've got my product rule, addition pairs with multiplication. So I can rewrite this as a single natural log statement. I've got, as my argument, I've got x squared times x plus 5 to the 1/3 power. I could leave it like that, or I could say, you know what, that rational exponent means radical. So I could rewrite this as natural log of x squared times the cube root of x plus 5. Either one of these results is going to be fine.